Sorry for a sort of jump. My phone overheated and the video stopped and I kept talking for a couple of minutes. So we're going to have to go back over some stuff again. So I think I got as far as just saying these are the unsaturated and the saturated fats. Now, the actual triglyceride, the actual molecule that you have in a fat or an oil, you take, you've got your glycerol and your three fatty acids, and we form an ester link between each of them. So we're going to be taking the OH and the COOH. We're doing a condensation reaction between each of them. So we're going to lose 3 molecules of water in total, and we get to this thing here. So this is the triglyceride. So this is the kind of molecules that you find in actual animal products and plant products, in the fats and the oils. And so I hope I'm not repeating myself here with these bits, but so fats, from which generally come from animals, they're usually unsaturated. They tend not to have any branching in that fatty acid chain. That means the chains can get quite close to each other. You get strong intermolecular forces, relatively strong. They're van der Waals forces, and so they tend to have higher melting points. The oils, which generally come from plants, you've got unsaturation. You've got those double bonds. That often this is the E isomer. They're often Zs, which causes the chain to sort of kink round. So if we have this one going down and round, so they're not straight, there's sometimes some branching. That means the chains can't pack as close together. So we've got weaker van der Waals forces, and that gives them the lower melting point. So they've got different uses. Oils and fats have different uses, used in cooking differently. But these are usually a lot healthier, and that's largely down to those double bonds. It means your body can actually digest them and break them down, because we've got this long unreactive carbon chain. Whereas in the unsaturated fats, there's actually something you can sort of grab onto, some sort of reactive unit that you can actually start to digest. Okay, so we're now going to look at the uses. And so one really important one that you have hopefully been coming into contact with multiple times every single day, is what happens if we react this with some sodium hydroxide. Now we need 3 equivalents of sodium hydroxide, because we're going to be cleaving 3 ester bonds. We're going to be doing 3 hydrolysis, base hydrolysis. We're going to break apart each of those. Now, the glycerol is the sort of alcoholic end. It does end up with a hydrogen on it. So when we do this, we get the glycerol back. Just draw this out. And then we get the sodium salt of each of these fatty acids, or the acid unit. So we get R1, we get R2, and we get R3. Na plus, Na plus. So typically the ones you're going to come across, they're all going to be the same as each other. So R1, R2, R3 would be the same. So you could just do 3 times one of these. But just for completion, I showed each of 3 of these. So the sodium salts of a lot of these fatty acids, they are used as soap. And the reason why they're really effective as a soap is you've got, if we just sort of draw the molecule out, and how a biologist might, sort of roughly doing things, we've got one end and then we've got a tail. Now this end has a charge. We've got, or charges, we've got Na plus and O minus, and then we have an apolar, we have an uncharged, we have a fat, lots of CH's end. So we've got a highly polar, a very polar end, and an apolar end. And some people doing biology might recognise this from your cell membrane stuff. But you've got an end that's highly soluble in water because it's polar, and an area that's very fat soluble. So let's say you've got a big blob of fat,